All right, welcome to The Explainer. Today we're going to tackle one of the most audacious, truly mind-bending, and weirdly elegant ideas in all of science. We're going to explore a concept that takes the strange rules of quantum physics and just follows them to their most incredible conclusion. The idea that every single possibility is real.
So let's just jump right in with a question that gets to the very heart of this. Think about it. What if every path you didn't take was actually taken? I'm not talking metaphorically. I mean, what if it happened in a physically real alternate universe that literally just split off from ours? That, right there, is the wild premise of the many worlds interpretation.
Okay, so to even begin to understand how physicists got to such a radical idea, we've got to start small. I mean, really small. We have to go down to the quantum level, where the rules of reality, well, they're nothing like the world we see around us every day.
Right at the core of this whole mystery is a principle called superposition. Now, forget everything you think you know, like a particle being here or there. At the quantum scale, a particle can exist in a combination of all of its possible states at the exact same time. It's not an either-or deal. It's more like a both and, well, everything else kind of situation.
The famous double-slit experiment is the perfect way to picture this. Imagine you're firing tiny particles one by one at a wall with two slits in it. You think they'd just pick a slit and go through, right? Nope. They act like a wave and create this ripple pattern on the other side, as if each and every particle went through both slits at the same time. It's one of the cornerstones of quantum physics. It's totally proven, and it is just deeply weird.
But hold on, because this is where the mystery gets even deeper. What happens if we try to peek, If we put a little detector at the slits to see which path the particle actually takes? I mean, you'd think we'd just be confirming what's already happening, right? Well, what actually happens is so much stranger.
And yeah, that simple act of looking, of measuring, it leads us right into one of the biggest headaches in all of physics. It's called the measurement problem. And honestly, it's the central paradox that every single interpretation of quantum mechanics has to try and solve. So, the instant we try to observe which slit the particle goes through, poof, that beautiful wave pattern just vanishes, gone. Instead, we just see two boring old lines, like the particles were just going through one slit or the other all along. It's as if the very act of looking forces the particle to, abandon all its other possibilities and just pick one.
And that, right there, is the huge disconnect. See, the fundamental math of quantum mechanics, the Schrödinger equation, it describes this smooth, wave-like thing where all the possibilities exist. But our real-world experience, what we actually measure, always shows us just one single concrete outcome. So the math is screaming all possibilities, but reality just whispers back, nope, just this one.
To really show how bonkers this paradox is, the physicist Erwin Schrödinger came up with his famous thought experiment about the cat. You probably heard of it. Basically, you have an atom that's in a superposition of both decaying and not decaying, and its state is linked to a vial of poison in a box with a cat. So if you follow the math, the cat's fate is tied to the atoms, which means the cat itself is in a superposition of being both alive and dead until you open that box.
So this is the crucial question, right? How does all this quantum weirdness, this mush of all possibilities, suddenly snap into the single definite reality we experience every time we look? I mean, when we open the box, the cat is either alive or it's dead. It's never both. So why? What's going on there?
Well, the answer that pretty much dominated physics for most of the 20th century is known as the Copenhagen interpretation. It gives us a direct answer, but as we're about to see, it's maybe not the most satisfying one.
The Copenhagen interpretation basically just adds a new rule to the game. It says that the act of measurement does something special. It forces that wave of all possibilities to just collapse, randomly, into only one of them. The superposition is broken, and reality just picks one outcome.
But, this whole collapse thing has always felt a bit like a patch. A lot of physicists see it as an artificial rule that was just tacked on, not something that came naturally from the theory. And it raises some really awkward questions, like what exactly counts as an observer? Is it a person? A camera? A single dust particle? The theory doesn't say. It just draws this weird, arbitrary line between the quantum world and our normal world.
So it was this frustration with the whole collapse idea that led a young physicist named Hugh Everett to come up with a totally breathtaking, really radical alternative back in 1957. He basically said, hey, what if we just get rid of the collapse idea completely and just trust the math, the original math?
Everett asked this really profound but simple question. What if the wave function, that thing describing all the possibilities, what if it never collapses? What if we just take the math at face value and assume it applies to everything all the time, including us?
And the result of that question is the many worlds interpretation. It says that when a measurement happens, reality doesn't just collapse down to one state. No. Instead, reality itself branches. Every single possible outcome of that event becomes real, but each one happens in its own brand new parallel universe.
Okay, let's bring it back to the cat, because this makes it really clear. In the old Copenhagen view, opening the box forces a choice. The cat is alive or it's dead. But in the many worlds view, opening the box creates two universes. In one of them, you see a live cat, and in the other, another version of you sees a dead cat. Both outcomes happen. They're both real. So in this picture, reality isn't a straight line, it's not a single timeline. It's more like an endlessly branching tree. And every single time a quantum event happens, an atom decaying, a particle going left instead of right, the universe splits, creating whole new branches, whole new parallel histories where each possibility plays out.
Now this is, without a doubt, an absolutely astonishing claim. And as you can probably guess, it has been the subject of some really intense debate in the physics community pretty much since the day it was proposed.
And the critics, they raised some really strong objections. I mean, first, just the sheer number of universes seems to fly in the face of Occam's razor. The idea that the simplest explanation is usually the best one. Second, if we can't communicate between these worlds, how could we ever test this theory? It seems impossible to prove or disprove. And then there are these really deep questions about probability. Like, what does it even mean to say there's a 50% chance of something if both outcomes are guaranteed to happen somewhere? And as you can see from this poll of quantum experts, the field is still really divided. The old Copenhagen interpretation is still super popular, but many worlds has been gaining a lot of ground. It's especially popular with cosmologists, the people who study the entire universe. And why is that? Well, think about it. You can't have an observer standing outside of the whole universe to collapse it. Many worlds gets rid of that problem entirely. It lets you apply quantum mechanics to everything, no outside observer needed.
So the big question is, why don't we feel ourselves splitting into different versions? Well, supporters of many worlds have an answer for that too. It's a process called quantum decoherence. The best way to think about it is like this. Each branching universe is like a radio signal on a slightly different frequency. The moment this split happens, they can't hear each other anymore. They're no longer tuned in. All the interactions with everything in their own environment, air molecules, light, everything, it instantly isolates them. And that's why we only ever experience our own single, consistent timeline.
So what's the big takeaway here? What does all this matter? Well, the many worlds interpretation offers this really elegant way out of the measurement problem. And it does it without adding any weird new rules to physics. It gives us a picture of this vast, branching reality that just evolves perfectly, according to one simple equation. The only price we have to pay for that mathematical beauty is accepting that the universe is, well, infinitely larger and more crowded than we ever imagined.
And that leaves us with one last, really provocative thought. Yeah, many worlds sounds like something straight out of science fiction. But the main alternative, the Copenhagen interpretation, says that the universe behaves one way when we aren't looking and then fundamentally changes its own rules the instant we do. So, when you're faced with those two options, which one is really the stranger idea?